Okay, so as we constructed the purity check matrix of the Hamming code inductively, so we can write it like HR is equal to 0, 0, 0, then one vector 1, 0, 0, 0 vector, all one vector, HR minus 1, HR minus 1. Now size of this matrix is, remember, R cross 2 raised to power R minus 1. So normally you know that um, size of purity check matrix is n minus k cross n. So n is here, 2 raised to power r minus 1, and rn minus k is equal to r. So k turns out to be n minus r, which is 2 raised to power r minus 1 minus r. This is the dimension of the Hamming code. Okay, and minimum distance turns out to be 3. Now one can verify that this code is perfect by checking the sphere packing bound, which is m times summation I is equal to 0 to t. T is here greater than 0, d minus 1 by 2, and so d is 3, so we know what is the value of t. T is 1 here, so I is equal to 0 to 1 and choose I. You can compute what is right hand side is 2 is for 2r minus 1, and left hand side you can compute from these parameters n, k, d. So I leave it as an exercise for you to verify that this is a perfect code. Now there are certain properties of this code. Obviously Hamming code is a perfect code, and as I mentioned to you, so k is 2 raised for r minus 1 minus r, right? That is your dimension. D is 3, t is 1. Here is an example. If you take h3 is equal to 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1. So this is a purity check matrix, and the size of the matrix is 3 cross 7. Okay, so length is 7 here, r is your 3 here, right? This is your r. So you know what is k actually. K you can compute from formula 2 raised to r minus 1 minus r. Okay, so that means it is 4. Now if x is a vector which is 1 1 0 1 0 0 1 belongs to C, we know that x is a code word. We can check it by taking hx transpose equal to 0, the definition of the purity check matrix. And if suppose y is a receipt vector as 1 1 0 1 0 1 1, then we compute the syndrome. Syndrome of a Hamming code turns out to be a column vector in the purity check matrix. Now if you look at this column vector, nothing but the 6th column of the purity check matrix, 1 1 0. That means the error is in the 6th column. You just flip the 6th position and you can correct the error. So in the y vector, in the y receipt vector, you just flip the 6th position, this one to 0, and you get x. Okay, this is how you decode it. It's really very straightforward. Now we can generalize this procedure to ternary code. When q is equal to 3, we need to keep in mind any two columns of h are linearly independent. Okay, so our space is now g3 raised to power r. Purity check matrix is r times 3 raised to power r minus 1 divided by 3 minus 1. Okay, we need to make sure that no two columns are multiples of each other. Okay, so for example, if q is equal to 3 and r is equal to 2, we get the following matrix: 0 1 1 1 1 0 1 2. And if r is equal to 2, q is equal to 11, we get the following matrix. Okay, in general, a query Hamming code has the following parameters: length is q raised to r minus 1 divided by q minus 1. Dimension is q raised to power r minus 1 divided by q minus 1 minus r, and minimum distance is 3. This is the most general parameters of the Hamming code. So I leave as an exercise for you to actually construct the parity check matrix in general for a q-ary Hamming code. Okay. Now another very important code is the dual code of the Hamming code, which is known as simplex code. So parameters for the binary code are 2 raised to r minus 1, k is equal to r, and minimum distance ought to be 2 raised to r minus 1. For example, if you look at the matrix here in the binary case, you can see that each vector is of weight 4 here. Okay, weight 4. This is also weight 4, this is also weight 4, and even if you take a combination, you get a vector of weight 4. Okay, so when r is 3, so the distance turns out to be 2 raised to r minus 1, which is 4 in this case. Okay, so this is the property of the simplex code. Distance between any two vectors is fixed in the simplex code. So a general simplex code, q-ary simplex code, is described by this matrix. That's all for today. In the next class, we are going to look at the construction of Gole code, and we will use a very powerful concept in number 3 known as quantity residues to construct the code.